So why does all of this matter? Well, as we said previously, every chemically different hydrogen or carbon will have its own peak. All right, so what happens once we make up a sample and put it into our instrument? Well, we start by exposing the sample to a magnetic field. And that magnetic field contains all of the possible delta E's that we could need to interact with our sample. After we do that, we turn off the field and record the signal that the molecule gives off. Now, at this point, we don't have all that usable data. What do we have at this point? Well, at this point, we have something that's known as an FID. And this is an example of an FID. A free induction decay. And that's this piece on the left. Now, for some people who are NMRs all they do, they can actually look at one of these FIDs and tell you if it looks okay. They might not be able to tell you much about the compound, but they can actually tell you if everything looks okay. But for what we need the actual spectrum, which is going to end up looking something like this. And in order to get there, we need to take the FID and do what's called a Fourier Transform. And I've just pulled up the Wikipedia entry for the Fourier Transform, and you're welcome to read as much as you want about it. As you can see here, Fourier Transform is a fairly complex mathematical operation, but any of the software that's designed for NMR spectroscopy does this operation in about a second or two. And what that gives us then is our actual spectrum that we can look at. So that's our third step that we can add in here, is the Fourier transform of data. So what we're going to end up with now is an actual spectrum, which will have peaks. But before we look at that, we want to talk about what are the things that determine where peaks appear. And right now, the things that we're talking about that help us to figure out where peaks appear, these apply both to proton NMR as well as carbon NMR. Right now, we're going to be focusing on carbon NMR. I tend to do that first because there's a few things that are common to both proton and carbon NMR in terms of understanding the theory and the interpretation. But there's also a few things that are specific and only apply to proton NMR. So what we do is we learn sort of the basics on carbon NMR, and then once we've learned those, we can move on to proton NMR, which is more complex, and we have to add a few new things in order to understand it. So again, our question is, what determines where the peaks show up? Well, it's basically determined by electron density. So if we have an atom that has high electron density, what those electrons do is that means that the electrons shield the nucleus. Because the nucleus is shielded, it requires more energy. And more energy and chemical shift, which is a term we're going to define in a few minutes, are actually inversely proportional to each other. So we get a lower chemical shift. If an atom has low electron density, then we say that the nucleus is deshielded. It's not shielded. Because it's not shielded, we could think of it as being more exposed. It requires less energy. And less energy leads to higher chemical shift. So what do we mean by low and high electron density? Well, what you'd want to think about, what if we attached a fluorine? So let's say we had methane. And then let's say we replaced one of those hydrogens with a fluorine. Well, fluorine we know is electronegative, and it pulls electrons away from the carbon. So by replacing that hydrogen with a fluorine, we've decreased the electron density on that carbon. What have we done to our chemical shift? So by doing that, putting an electron withdrawing group on there, we lower the electron density, and we should end up with both the carbon as well as the hydrogens that are attached to it should both show up at higher chemical shift. And if we look those up, it's actually a very significant effect. Again, we haven't defined any of these terms we're using yet. Don't worry about them. We will define all of these shortly. But one of the hydrogens in methane, if we're looking at a proton NMR spectrum, has a chemical shift of 0.232 ppm. What about fluoromethane? Ends up being much higher, about 4.10 ppm. So we can see that by changing even one atom, we can end up with a pretty significant difference in chemical shift. And if we added even more fluorines, so let's say we had 3 of them on there, we now get a chemical shift for that hydrogen of around 6.25 ppm. So even less electron density, even higher chemical shift. All right, so what are these terms that we're using here? What is chemical shift? Because that's a term we're going to use for both proton and carbon NMR. Chemical shift is literally the position or the energy at which a nucleus absorbs. Now, initially when an instrument takes a spectrum, it comes up with a value in hertz. And these values end up basically being relative to each other. So we have to do 2 things to make this data useful. The first is that we need a reference. And so the compound we use as a reference is a silicon with 4 methyl groups on it. So silicon has an electronegativity of 1.8 compared to carbon at 2.5. So the carbons in this compound, known as tetramethylsilane, which we abbreviate as TMS, these carbons, as well as their hydrogens, are highly shielded because they're surrounded by electron donating groups. And so this compound TMS is referenced to 0 hertz. The other reasons we use this compound as a reference is because it's got the 4 equivalent methyl groups, it gives us a very strong signal. Because it's so highly shielded, it's not near most other compounds that we deal with. And finally, it boils at around 26 degrees Celsius, which is about 80 degrees Fahrenheit. So it's really easy to get rid of. It won't contaminate your sample because it'll, just at room temperature, even, it could boil away. Now, the problem with using hertz, and that's how the instrument normally gives us the data initially, is that using hertz gives us values that are dependent on the instrument that we use. So in other words, if we have a 300 megahertz magnet and a 400 megahertz magnet, they're going to give us different chemical shift values. And so the way that we deal with that is we use this delta, or ppm, parts per million, ppm scale. We calculate that as the observed shift, which is in hertz, and we divide it by the frequency of the NMR, which is in megahertz. And these values that we get, the ppm values, are independent of magnet strength.